Hello and welcome. This is part 4 of the electricity and magnetism videos. In this video, I'm going to talk about the relationship between electric field and electric potential and demonstrate this using a simple example like a charged rod. So here's the plan of what I'm going to be showing in this video. So the example is a charged rod. This will carry a uniform charge of, let's say, Q on it. A uniform charge. This is on the x-axis. And the thickness or the radius is irrelevant, but the length is 2a, so that we have half of it on this side, a, and the other half on the negative x side. Okay, this is x equals a right there. And this will be x equals negative a. So I wish to find the electric field at a point y above the midpoint here. So this is the y-axis. Now, I already worked out this problem before in one of the videos, probably in video 1, but only the electric field. Now I'm going to find the potential as well. So here's the plan. 1, find the electric field at point P. Let this be point P. Using, integration. So basically, we're going to consider an infinitesimal amount of charge right here, which is in a length dx, infinitesimally small portion or section, which will have a charge dq, of course. And because of this dq, it's a positive charge, we'll have an electric field pointing away from dq in this direction. Let's call this dE. And this makes an angle here, theta, which is also equal to this theta here. So this point is x away from the origin, which makes this side equal to square root of x squared plus y squared. So that dE is coming from each little segment carrying a charge dq, right? I mean, according to Coulomb's formula, or for electric field due to a point charge, we have dE equal to this constant 1 over 4 pi epsilon 0 times that charge divided by the square of the distance between the source and the observation point, point P. So if you take that square, that is x squared plus y squared. Okay, so we have to take into account all these dEs coming from all around over the surface, over the object here, from negative a to positive a. That means an integration, right? So that's the method here, finding electric field using this method. All right, and then consider the limits when you're really close to the charge. This means y will be much smaller than a. And in that limit, practically the charge rod will be of infinite length. So infinite line of charge limit. And then the other limit where y is so large, then the line of charge looks like a point charge. I'm going to call it point charge limit. Okay, and I'm going to repeat this for electric potential. find the electric potential at P and consider the same limits. Check the above limits. And then, well, number 3 is calculating electric potential using the same method, meaning integration. The only difference will be dV at point P will be 1 over 4 pi epsilon 0 dq over square root x squared plus y squared. Now this assumes, of course, that when y goes to infinity, v is 0. All right. We're going to come back to that point later. Now, method 4 will be a little different. We're going to go back to the very beginning of the chapter where we talked about electric potential, energy and electric potential, and came up with this formula, which gives you the potential difference between points 1 and 2 as an integral E dot dl. So can we apply this to this problem? That's what we're going to investigate in this section. And then finally, going the other way, starting from potential, how do you find electric field based on this formula here? The negative gradient of the electric potential gives you the electric field vector. So let's test all this for this example. All right, so we're going to need to find the electric field, the potential. We're going to check this integral here, E dot dl, and then we're going to use that derivative. Let's make a table. Okay, and then we're going to check our limits. Limits when y is less than a, and for a very large y value. Okay, so let's try to fill this table. All right, so let's start with reviewing the electric field calculation. Let me open up a new whiteboard. So here's our charge. Here's the y-axis. Here's the point. Now, due to a charge at infinitesimal dq right here, the electric field will be pointing this way. But if you think about the symmetry, for every charge on the right-hand side of x equals 0, you will have another charge on the left-hand side. Say for this one, you will have an equal dq on the other side at negative x, right? And due to that, you will have a point vector, a vector pointing this way. Now, due to symmetry, these two angles are the same. Therefore, their x components will be pointing in the opposite direction, and also they will have the same magnitude. And these will cancel each other when you add two vectors. Their x components will cancel, but the y components will not. All right, so we'll actually consider, this was dE, remember, what we really need is dE cosine theta. All right, so let's write this down. This will be our integrand, all right? So 1 over 4 pi epsilon 0. Now, in the denominator, I will have x squared plus y squared, of course. This is y. This side is square root of x squared plus y squared. Now in the numerator, I'll need dq. If the total charge is q and the length is 2a, then the charge density will be q divided by 2a. All I need to do is to multiply that charge density by dx to find how much charge I have here, dq. And I'm going to move that dq along the x-axis. X will change, but the value of dq will not change. It's coordinate independent. It's a uniform charge distribution. Now this is dE. Now I need to multiply it by cosine theta, which is y divided by square root x squared plus y squared. So the thing I'm going to be integrating is 1 over 4 pi epsilon 0 q over 2a integral of, what is it? Actually, y is like just a constant for this integral, okay? I'm integrating over x. So y is here. The integral will be from negative a to positive a dx divided by, now I have this thing here, squared, square root, and then times that. That will be 3/2. All right. Now you can either look this up on an integral table, or if you don't want to do that, you can actually find it using some substitutions, right? Now this type of integral, where you have x squared plus y squared, you could use a trigonometric substitution, like this theta here. Use that. So tangent theta, for instance, tangent theta is x over y, right? Which means x is equal to y times tangent theta, y sine theta over cosine theta. So take the derivative of this, dx will be y, a constant, times sine derivative is cosine. So cosine times cosine, cosine squared, minus sine times derivative of cosine, which is negative sine. So I have a negative sine squared, makes positive, divided by the square denominator, cosine squared theta. And the numerator is 1, therefore dx, there's a d theta here, of course, dx will be equal to y d theta divided by cosine squared theta. And I will need the quantity here, x squared plus y squared, and that will be y squared sine squared theta over cosine squared theta plus y squared. If you equate denominators, this will be y squared cosine squared over cosine squared, and cosine squared theta plus sine squared theta is again 1, and I will end up with y squared times 1 over cosine squared theta. So if I take the negative 3/2 power of this, what will I get? I will get cosine cubed theta divided by y cubed. So if I put these together, my integral is what now? So 1 over 4 pi, 4 pi epsilon 0 q y divided by 2a, and then what I have is the integral of, okay, dx, that's y d theta over cosine squared theta, and then here I will have cosine cubed theta, right, over y cubed. So this is nothing but 1 over y squared cosine theta d theta. Therefore, 1 over 4 pi epsilon 0 q over 2ay, right? This is y squared y, 2ay. The integral of cosine theta is sine theta, right? Sine theta. And what is sine theta? That's x over square root x squared plus y squared. If I plug in the limits now, x goes from negative a to positive a. One over 4 pi epsilon 0 q over 2a y. Plug in the first limit, upper limit, a over a squared plus y squared, minus, now plug in the lower limit, negative a over, same thing, a squared plus y squared. So a minus negative a makes 2a's, and then I have 2a in the denominator here. They will cancel out, and the electric field will be equal to 1 over 4 pi epsilon 0 q, total charge, divided by y, and then here you have square root a squared plus y squared, all right? And it will be pointing in the positive y direction. So if you want to write it as a vector, put an arrow on top of e, and then include a unit vector here along the y direction, j hat. Okay, so that's our electric field. Let's fill that table. Let's start filling this. So here we have 1 over 4 pi epsilon 0 q divided by y square root a squared plus y squared. Now let's check those limits. Let's check those limits. Okay. So the first limit is y is much less than a. You're really close to the charge. This is when the charge looks like an infinite line of charge. Okay. So in other words, y over a is very small. Okay, so here I'm going to try to obtain y over a. How do I do that? I can factor a out. So e can be now written as 1 over 4 pi epsilon 0 q over y times A square root 1 plus y over A squared. Okay, so you're really close to A. And let me do one more thing. Since it's an infinite line of charge approximation, it's better to use the charge density here. Use the charge density, call it lambda, q over 2a. I mean, we used this in the beginning without naming it. Now I'm going to call it lambda. So I have q here. So I'm just going to add, I'm going to add 2 here, another 2 right there, so that this q over 2a will be my lambda. And also here I have this function 1 plus y over a squared to the power negative 1/2. Like if you would expand this around that small number here, the first couple of terms would be 1 minus 1/2 y squared over a squared. It goes like this, right? But if it's too small, I can just ignore it. Y squared is even smaller. And it's pretty much 1, all right? So this doesn't bring me anything new here. So what do I get then? E will be in that limit. There's 2 here, there's 4. So let's make this 2. E will be equal to lambda over 2 pi epsilon 0 divided by y. Okay, that's my limit when y is very small compared to a. Now the other limit is when you're really far from the charge, y is much greater than a. All right, so in this case, a over y is very small. This is the point particle or point charge approximation. Point charge approximation. And this was the infinite line approximation. So in this case, if you go back to that formula here, what can you do? You can factor y out. So E is exactly equal to q over 4 pi epsilon 0 y, and I'm going to take another y from the square root, y squared. So here I will have 1 plus a over y squared. For the same reason, I can take this to be equal to 1, and this will become q over 4 pi epsilon 0 y squared. Okay, so if you're really far, your observation point is really far, this little rod becomes like a point, you know, at that distance. So I get the Coulomb expression. So let's write these in the table again. All right, now I'm going to apply the same thing to electric potential. Okay, so in these limits, what do I have? When you're really close to the charge, that's y less than a, much less than a, then we have lambda divided by 2 pi epsilon 0 y, and in the other limit, 1 over 4 pi epsilon 0 q over y squared. That's the point charge limit. Okay, so that's the method, all right? Let's apply the same method to electric potential, all right? So let's open up a new whiteboard. So again, here I have the line charge, negative A, positive A on the x-axis. Here's the y-axis, and I'm y away from the charge, all right? So how do I do this? Now, for a point charge, the potential is given by this formula. This we've seen in the class. Q over R, where R is the distance from that point charge. That's for a point charge. But here we don't have a point charge, but we can use an infinitesimal charge and think of it as a point charge exactly the same way. So this is equal to Q over 2A times dx. One difference though, electric potential is a scalar quantity, so I don't have to worry about the angles here. So the electric potential can be directly found from the expression here. dV will be equal to 1 over 4 pi epsilon 0 dq, which is Q over 2A dx divided by the distance here. That's square root x squared plus y squared. Okay, if you just integrate this, you have your V. So V will be 1 over 4 pi epsilon 0 Q over 2A. Integral will be from negative A to positive A dx divided by x squared plus y squared. So again, let's apply a trigonometric substitution. X equals y tangent u. All right. So dx will be y du, just like the previous case, over, what was it, cosine squared u, and 1 over square root x squared plus y squared will be 1 over y squared sine squared u over cosine squared u plus y squared. Okay, so this will give us cosine u over y. So the integral is 1 over 4 pi epsilon 0 q over 2a. I'm not writing the limits for now. Let's just use indefinite integrals. Dx is y du divided by cosine squared u. And then this factor here is cosine u over y. Just checking, did I forget any y's here? That's one more. Okay, I think that's it. So basically, my integral is q over 2a. My integral is du over cosine u. Okay, so I will need another substitution here to solve this integral. So I take 1 over cosine u, and then let's add a tangent here, which is sine u over cosine u, and call this a nu variable, call it phi, right? The derivative of the left-hand side, now you will have cosine derivative is negative. So I have negative sine u divided by cosine squared u. Then there's another negative here. Okay, so that makes positive, right? Plus, okay, we already saw this. This gives us 1 over cosine squared u. du is equal to d phi, but the left-hand side is actually, if you factor 1 over cosine u out, this is just 1 over cosine u plus sine u over cosine u. That is what we called phi. So 1 over, let me just rewrite this here, du over cosine u becomes d phi over phi. And the integral will be the logarithm function, right? Plus some constant, but I'm going to worry about that later. So basically, we need logarithms here, natural logarithm. And phi is this. So if I can write what phi is equal to in terms of my x and y variables, I'm done. So phi will be equal to 1 over cosine u. So u, tangent u was x over y. So this is pretty much u here. This is my u. And therefore, 1 over cosine u is y over 1 over cosine, I'm sorry, the other way around. So cosine u is y over square root of that, but 1 over cosine u will be square root x squared plus y squared divided by y plus tangent u, which is x over y. X over y. So all I have to do now is to plug in those limits. So v will be equal to 1 over pi epsilon 0 q divided by 2a logarithm of this plus x divided by y. And the limits are from x equals negative a to positive a. Okay, so I'm going to plug the upper limit and then subtract the one with the lower limit. So ln a minus ln b is ln a over b. So if I do that, q over 2a, I will have natural logarithm of. Now, if I divide this by the same thing, the y's will cancel. I just need to use the numerators. Instead of x, I'm going to use a. So a squared plus y squared plus x, or plus the a, I'm sorry, divided by, same thing with the negative now, a squared plus y squared minus a. Okay, this is our potential at y. So let's copy this. Let's copy this to the table. So here's the table. Okay, zoom out. All right, right here, 1 over 4 pi epsilon 0 q over 2a natural logarithm of a squared plus y squared plus a divided by square root of a squared plus y squared minus a. All right, so this is the electric potential. Now what's next? To find the limits. All right, so let's try to do that now. Let's go back to that, where was I? Right here. Let's scroll down. Okay, this expression here, zoom out a little bit. The two limits that we want to consider are A, when y is much greater than A, and then when y is much less than A. Okay, so let's do the small a limit first. So we have expressions like this: a squared plus y squared. And this is equal to, if you factor a out or y out, you will get a squared over y squared plus 1. And remember, a over y is small. Therefore, this is just y. Okay, so our potential in that limit converges to 1 over 4 pi epsilon 0 q over 2a logarithm of I'm just checking a over y squared is small, yeah. Y plus a divided by y minus a. Okay, let's do that trick one more time. This is then equal to, if you factor y out, you will have 1 plus a over y. And here you will have 1 minus a over y, which is equal to ln 1 plus a over y minus, right? The logarithm of x over y is x minus y. So ln logarithm of x minus logarithm y. So ln 1 minus a over y. Okay, again, a over y is small. So this will be approximately equal to a over y. I'm just using this. Logarithm of 1 plus a very small quantity, call it w, will be equal to w. So this will be equal to then negative a over y. A over y minus negative a divided by I is 2ay. So in this limit, b becomes 1 over 4 pi epsilon 0 q over 2a times 2a over y. And the 2a's cancel. We get the simple expression which you would find, which is what we started with, right? The electric potential due to a point charge. Again, this expression, recall from the lecture, is when you assume the potential is at 0. at infinity. Actually, this formula dictates that 1 over y goes to 0 anyways. So I'm going to copy this to, before I do that, let's worry about this now, the other limit. When you're really close to the charge, when y is much less than a. Now you can do the same trick. I mean, you can take this expression and instead of factoring y out, you can factor a out and do things like this. But if you do that, you're going to get into trouble. Okay, so basically you're going to have logarithm here. If you factor a out, I mean, get rid of the a's, then you will have something like ln of, what is it, 1 plus y over a squared, square root of that, plus 1, and then in the numerator, same thing, denominator, same thing with negative, y divided by a squared, minus 1 though. And this creates a problem now, because when y over a is so small, this is 1 minus 1, you get an infinity. Okay, that's not good. So we're going to be stuck if we do it like this. And that's because we're considering pretty much an infinite charge. Okay, infinitely long charge. If we just take this answer for generic a and y and try to apply that idea of limiting, we're going to get into trouble. So we have to come back to this later. All right, so I'm going to mark these in the table first. So this is, let's put a mark there, but in the other limit, yes, it's simple. Over 4 pi epsilon 0 q over y. Okay, so how can we find that limit then? If this doesn't work, maybe this calculation will help us here. The integral of E dot dl. Okay, that's the next item in our list. E dot dl. So let's open up a new whiteboard here. Okay, so v1 minus v2 is an integral from, so 1 and 2 are points. In general, you will have this expression, E dot dl, where dl is displacement along the path you choose to go from 1 to 2. So in our case, now assuming we already know what the electric field is, how can we find the potential difference, v1 minus v2? That's the method here, okay? So here's the charge again, and here's the y-axis. Now let this be point 1. So I'm actually y1 from the charge, and then here's the second point, which is y2, okay? So point 1 and point 2, and I'm going to go from point 1 to point 2 along a straight line, which is the easiest one because I know that electric field is parallel to that increment. So dl will be just a straight line. It's a line integral. Okay, so let's remember E. This was 1 over 4 pi epsilon 0 q over 2a. No, not q over 2a. Q over y square root a squared plus y squared. This was the electric field. Okay, so this will go to the integral. dl is nothing but dy, or the vector is nothing but dy times j hat, and j hat dot j hat is just 1. So this integral is, let's take q out of the integral, q over 4 pi epsilon 0. Integral will be from y1 to y2 dy divided by y, right? And then a squared plus y squared. So we got another trigonometric substitution, right? Because of the square root there. So let's do that. Instead of y, let's use a tangent u. All right. So in that case, dy will be equal to, okay, let me just resume for a second, pause for a second. Okay, sorry about that. I had chicken in the oven. All right, so dy will be a du divided by cosine squared, what? U, right? All right, so, and square root a squared plus y squared is equal to a over cosine u. Okay, so this integral becomes what? Q divided by 4 pi epsilon 0. I'm not going to write the limit now. I'm going to do that later. So dy will be a du over cosine squared u. And then 1 over y a sine u over cosine u. Okay, and then what is left? 1 over square root that thing. So 1 over a over cosine u. Okay, so let's simplify this. These, how many a's we have? A du from here, and the other from y, 1 over a tangent u. Okay, and then the square root also has an a. So this cancels that. Cosine squared u, cosine u, cosine u. So we get rid of cosine u's as well. Okay, so q divided by 4 pi epsilon 0. There's an a here, right? And the integral of du divided by sine u. All right. So what is u anyways? U is, tangent u is y over a. Remember, this was a, and y is a point on the y-axis right there. So we're talking about y over a. This is y. This is a. So we're talking about this actually. All right. This is our u. This problem. That's u. Anyway, so the integral of du over sine u, cosecant u. To do that, we have to do a substitution. You can do it 2 ways. You can either do this, 1 over sine u, add a cosine u over sine u, cotangent u to it, and call it phi, right? And then try this substitution. Or you can do this. 1 over sine u minus, both work actually, cosine u over sine u, call this one phi. Let me show you both. So 1 over sine u, take the derivative now. This makes a negative cosine u over sine squared u from the first term. And the second term, I'm going to now have cosine. Its derivative is negative sine times negative sine. I'm sorry, negative sine times sine, negative sine squared u minus cosine u times derivative of sine, which is cosine, divided by the square of the denominator, sine squared u d phi, that is equal to not d phi, du equals d phi. All right, so simplify this a little bit. On the left hand side, you will have the negative 1 over sine u times this 1 over sine u. Why 1? Because sine squared plus cosine squared is 1, plus this cosine u over sine u. du equals d phi, so this is phi. All right, so using this substitution, the integral, what was the integral? Q over 4 pi epsilon 0 a. Let me just write the integral. D u over sine u becomes negative integral of d phi over phi. In other words, negative ln phi plus a constant, but we don't worry about the constant because we're going to plug in phi. Okay, so phi is right there. So the integral is negative ln 1 over sine u cosine u. This is the integral. Okay, what if you did the other way? Like, what if you subtracted the cotangent u? Let's see what would be different in that case. From the derivative, we'll still have negative cosine u. I'm just copying from the left-hand side. Sine squared u. On the right-hand side, there's this negative, which you carry, and then cosine over sine. It's going to give you the same thing, same derivative, but there's a negative there. So that's negative 1. There's already a negative here, which makes this positive. So 1 over sine squared u. du equals d phi. All right? So if you factor 1 over sine u, you will have here 1 over sine u minus cosine u divided by sine u. du equals d phi. And that is phi as well. All right. So same idea. It's just that we have a different phi, and the integral will not be negative. So we'll have the logarithm of our phi here, which is 1 over sine u. And the numerator, I will have 1 minus cosine u. Okay? So these two should be equal to each other. These two, I mean, should be equal to each other. And if you want, you can show that they're equal. You want to do that? So let's try. So negative ln. Carry this negative to the exponent here. So this will be equal to ln of sine u divided by 1 plus cosine u. Is that equal to this? 1 minus cosine u over sine u. What do you do now? We can cross multiply, right? Sine u times sine u is sine squared. And then this times that. 1 plus cosine u times 1 minus cosine u is equal to 1 minus cosine u squared. And that is exactly what it's equal to. The thing on the left. So they are equal, okay? So if they're equal, which one are we going to pick? Let's pick both. Okay, what do I mean by that? I mean, if you call this expression A, if you call this expression B, instead of picking A or B, I can do this. So A, for instance, is equal to A plus B over 2. Right? So this integral du over sine u is equal to 1/2. Write A now, ln 1 minus cosine u divided by sine u, and add b to it. B is this negative ln 1 plus cosine u over sine u. They share the same denominator, so we can simplify this now. Okay, so that's equal to 1/2 ln. This minus that, this goes in the denominator. Sine u's will cancel, and you will have 1 minus cosine u divided by 1 plus cosine. Okay, so this is my integral. Let's plug that in. Where is it? Right there. Let's plug it in there. Q over 4 pi epsilon 0. A times 1/2 logarithm of, okay, I already forgot, what was it? 1 minus cosine A? It was 1 minus cosine U. 1 minus cosine U divided by 1 plus cosine U. Okay, the final step, let's write down what cosine U is. Remember this, let's go back to our picture here. I think I marked already what U is there, right? So here. So from this picture, cosine U is what? It's equal to A divided by square root of A squared plus Y squared. All right, this red line here is equal to the hypotenuse of that triangle, which is square root Y squared plus A squared. So let's plug that in here now. One minus A over square root A squared plus Y squared divided by 1 plus A over A squared plus Y squared. So this integral will be equal to 1 over 4 pi epsilon 0. There's QA2, Q over 2A. And here I will have logarithm of, let's get rid of the denominators. So square root A squared plus Y squared minus A, right, divided by square root plus A. And the limits are from y1 to y2. From y1 to y2. All right, so remember this is equal to v1 minus v2. v1 means v at y1, v2 means v at point y2. I'm just going to plug those in here, and then I'm going to take y2 to infinity. Assume that when that happens, the potential is 0. Okay, same idea with the point charges. That's what we did at the beginning. So I'm going to do the same thing here, and I'm going to replace y1 with just y. It's going to become a function of y. So here I will have now, plug in the limit, 1 over 4 pi epsilon 0 q over 2a ln of a squared plus y2 squared, square root of that, minus a divided by a squared plus y2 squared plus a, minus, same thing with the lower limit, ln a squared plus y1 squared minus a divided by a squared plus y1 squared plus a. Okay, now check for a second if that assumption makes sense. Well, I said when y2 goes to infinity, we want 0 potential. So this here actually does go to 0, because for an infinite y, a doesn't matter. So it's like the argument of the logarithm function goes to 1, and ln 1 is 0, right? So this term actually goes away. It checks. So what is left is this one, negative, with a negative sign. Let's carry this negative onto the argument here. So this thing in the parentheses to the power -1. I'm going to swap the numerator with denominator. So my v1, which I'm just going to call v now, or v of y, will be equal to this term goes away, the first term. The second term, I'm getting rid of the negative, and I'm changing the numerator to the denominator. So I will have 1 over 4 pi epsilon 0 q over 2a. Remember, so far I'm not really imposing a condition on a and y. Okay, they're really arbitrary here. I only took y2 to infinity, and then y1 is just renamed to be y. And here I will have a squared plus y squared plus a divided by same thing minus a. Okay, that gives me the electric potential at an arbitrary point along the y-axis above the charge. That's the potential, okay? So if Q is a positive charge, potential will be positive. If Q is negative, it'll be negative, all right? So this is exactly the same result we got from the previous calculation, right? Let's double check that. So let's go back to that table. Here's the table. Let me zoom out a little bit. And in the table, we already filled out, we already filled out the potential here. Same expression, see? 1 over 4 pi epsilon 0 q over 2a ln whatever. So this checks. I'm going to put a check mark here. Same result. Same result as this. Now, I don't need to, if I get the same result, I don't need to do the limit thing again. Obviously, I'm going to check the same thing I'm going to get the same thing if I did the point charge limit when y is really large compared to a. Okay, now what about this? This is when you're so close to the charge, right? Now let's see if we can take care of that. Let me go back to that same, where was it? Was it this one here? Yeah, this one, okay. So, oops. So, in this limit, I'm getting the same formula, meaning V1 minus V2 is equal to the integral from point 1 to point 2 E dot dl, but use the version of the electric field which is already calculated under the assumption that you're really close to that charge. Remember, in that limit, E of y would be equal to the charge density, lambda, divided by 2 pi epsilon 0 y. This is the limit when what? Y is much less than a, the infinite charge limit, infinite line of charge limit. So if I use this expression in the integral, it's so simple. Check it out. So V1, the integral is simple, I mean. So V1 minus V2 will be equal to the integral from Y1 to Y2. I mean, the direction did not change, right? It's still upward. So it's a line integral along the electric field. Lambda dy divided by 2 pi epsilon 0 y, which is simply the logarithm of y. So lambda over 2 pi epsilon 0 ln y. The problem is something else, though. We still have this infinity here. Like, remember, I want to pick v2 as 0 at infinity. So if v2 has to be 0 at this, then I get in trouble because I will have natural logarithm of infinite. Okay, I'm going to have the same problem that I had before. In order to avoid that, then do not consider v2 to be 0 at y equals infinite. y2 could be any arbitrary number. Then assume v is 0 when y2 is some arbitrary number, call it capital Y. Okay? Then v1 minus 0, I'm just going to call it v. Potential of the point, of the point y. Then this integral becomes, or the result becomes lambda over 2 pi epsilon 0, natural logarithm of, upper limit is capital Y, just a constant, minus ln the variable y, or write it as lambda 2 pi epsilon 0 ln of y divided by y. Okay, that's the outer limit. That's what I'm going to put in the table now. Okay, zoom out. Where's the table? Right here. The result will be lambda over 2 pi epsilon 0 ln y over y. Okay, and you can use the same thing here. But the result here we did not obtain from the expression for v, but from the integral. Lambda over 2 pi epsilon 0 ln y over y. Okay, so what is left? The only thing left is this derivative, the gradient of v. Basically, if I take the derivative of v with a negative sign, do I get that? All right. So, I mean, actually, it's really easy if you just consider this one here. Q over y, the derivative will be q over y squared with a negative sign. Two negatives make positive, and you get already that. What about the first line here? You know what? I'm going to leave that to you. So, homework. Show that negative d over dy of this expression here, 1 over 4 pi epsilon 0 q over 2a logarithm of, let me not use square bracket here, a squared plus y squared plus a divided by a squared plus y squared minus a. Show that if you take a derivative with a negative sign, you will get the electric field on the left side. 1 over 4 pi epsilon 0 q over square root a squared plus y squared. Okay. The derivative of a logarithm is 1 over that, but you have to consider the derivative of the argument as well. So to do that, the simplifications should give you that result. I'm going to put a question mark here. Prove it. All right. So you can go from potential to electric field using the gradient. You can go from electric field to potential using the integral. And you can do all these approximations. Things get a little bit tricky when infinities are involved. Just be careful with that. And this is only for the line of charge. I'll probably make another video with a charge disk. Maybe the same approach, I can do it. Or maybe I can test it on the test, I don't know. All right, I'm gonna stop here right now, and I'll meet you in another video soon.